Look at the sun. It provides the energy required for life to exist, but it also operates as a violent nuclear reactor. It constantly emits ultraviolet, or UV, radiation, which are high-energy light waves that can damage living cells. It also blasts out the solar wind. The solar wind is a continuous stream of highly energized, charged particles ejected from the sun's upper atmosphere at supersonic speeds. With that constant barrage of lethal energy radiating in every direction, a planet orbiting nearby should be stripped bare and completely sterilized. Yet here we are, covered in oceans and forests. Earth survives because it operates a dual armor system. We are surrounded by a chemical blanket made of gases and encased within a physical, invisible magnetic bubble. Our habitability relies entirely on these two active defense systems working together to continuously repel the incredibly hostile environment of space. This diagram shows the chemical breakdown of our atmosphere. 78% is nitrogen, and 21% is oxygen. But the real heavy lifting for our planetary defense happens in the remaining tiny 1%. That thin sliver of trace gases handles the incoming cosmic threats. Moving vertically from the surface, we start in the troposphere. The troposphere is the lowest layer where all human life exists and weather patterns form. Right above it sits the stratosphere. The stratosphere contains ozone molecules that act like a chemical sponge, absorbing the majority of the sun's harmful UV rays before they can reach the ground. Higher still is the mesosphere. The mesosphere is a middle atmospheric layer where temperatures drop sharply and gases become dense enough to create intense friction. When physical space debris and meteoroids hit this layer at high velocity, that friction burns them up into harmless ash. Above that, we find the thermosphere. The thermosphere is a highly active, high-altitude layer where incoming solar energy causes temperatures to spike. Finally, the exosphere marks the outermost edge, slowly thinning out until it fades entirely into the vacuum of space. This thermal model demonstrates how that atmosphere manages heat. Sunlight passes through the gases and warms the Earth. As that heat radiates back upward, trace greenhouse gases, specifically molecules like carbon dioxide and methane, absorb the outgoing infrared energy and trap it near the surface. Without those specific trace gases catching the exiting heat, the global average temperature would drop to a freezing -18 degrees Celsius. Instead, it hovers around a comfortable 15 degrees. The atmosphere perfectly filters lethal light and regulates surface temperature. However, gases alone cannot stop the sheer physical mass and kinetic impact of the solar wind. If a supersonic stream of charged particles hits a static layer of gas, the gas eventually gets blown away. Earth needs a physical deflector to handle the brute force. That deflector is generated nearly 3,000 kilometers underground. The Earth's outer core is filled with churning, convecting liquid iron. As this molten metal flows, it creates electric currents, generating a massive magnetic dipole, a planetary magnetic field with opposing north and south poles. Looking at this 3D model, you can see how the field projects far out into space to create the magnetosphere. The magnetosphere is the region where our magnetic field dictates the movement of charged particles. When the solar wind slams into it, it hits a boundary area called the bow shock. The particles are forcefully redirected around the planet, sliding along an elongated, stretched section on the night side known as the magnetotail. A small fraction of those energized particles do get caught in the field. They travel down the invisible magnetic lines toward the north and south poles, eventually crashing into the upper atmosphere. When they collide with oxygen and nitrogen molecules, they release energy in the form of brilliant light. Those glowing auroras are actual physical evidence of our magnetic shield taking a high-energy hit, successfully absorbing the impact so the atmosphere below remains intact. To see what happens when that shield fails, we only have to look at Mars. Billions of years ago, Mars had a hot, churning core, an active magnetic field, and a thick atmosphere. Then, because Mars is much smaller, its interior cooled down, and the magnetic dynamo ground to a halt. With the magnetic deflector gone, the Martian atmosphere was fully exposed. The solar wind relentlessly slammed into the planet, physically stripping the gases away and scattering them into deep space. The Moon offers an even clearer picture. It has zero atmosphere and no magnetic field. Its surface is scarred by millions of craters from unhindered asteroid impacts, and it is continuously blasted by unfiltered cosmic radiation. If Earth's molten core were to suddenly freeze and our magnetic field vanished, the solar wind would immediately begin tearing at our sky. The ozone layer would degrade, the greenhouse gases keeping us warm would be swept away, and the surface would be completely sterilized by solar radiation. But our core is still spinning, and the magnetic bubble is still holding. Right now, the immediate threat to the atmosphere isn't coming from the void of space. By burning massive amounts of fossil fuels, human industrial activity is rapidly altering the delicate 1% of trace gases that maintain our global temperature. Deep underground and high above the surface, Earth's natural systems maintain a perfect, active balance to keep the hostility of the universe at bay. The only thing they can't protect us from is our own disruption of that balance.